Welcome back, learners. So now jumping to our first concept of the lesson, whereby we're going to be comparing the series circuit and also the parallel circuit. So to begin, we need to know what we're going to be comparing and how are we going to be comparing those variables. So we are going to start with cells that are connected in series, and then also we're going to compare those cells in series and also with them in parallel. So to begin, the total voltage, if you connect our cells in series, the total voltage being the potential difference is going to be equal to the sum of the voltages across each individual cell that is connected in series. Furthermore, when we are connecting these two cells, remember we're saying that if it's just one, it's a cell, but then once they are connected, more than one cell connected, it forms a battery. So therefore, we are saying the total voltage, or rather the total potential difference, is going to be equal to the sum of the voltages across each individual cell. So that means if one cell has a potential difference or a voltage of 1,5 V, and this other one being 1,5 V as well, we are saying that the total is going to be equal to the sum of the two cells that we have here. So that means the total voltage is going to be 1,5 plus the 1,5, which is going to give us the 3 volts, which is going to be our total voltage for the entire cell, only if they are connected in series. We are saying this. Each cell adds to the voltage available to the charges. Now, what then happens if these cells are connected in parallel? Because in series, we're saying each individual cell contributes to the total voltage of the circuit. In parallel, the total voltage or the total potential difference across cells connected in parallel is the same as the voltage of an individual cell. So now we're saying that in parallel, the sum, or rather the potential difference of each cell is going to be equal to the same as that one of the total potential difference of the entire circuit. So that means now that we have our two cells connected here in parallel, they are not connected one after the other. Remember, if they are connected in series, it's one after the other, as we can see on this diagram here. If they are connected in parallel, that means the voltage provided, or the voltage provided by this cell, if it's 1,5, it means also even the total circuit, it will have the voltage of 1,5, because the statement says the total voltage, which is the potential difference across cells connected in parallel, is the same as the voltage of an individual cell. So the total is equal to the individual cell. We are then saying that each charge gains voltage from a single cell. So that means the charges that are moving from one point to the other, they are gaining voltage as if they are gaining from one single cell. Now, what about then resistors that are connected in series? Resistors or light bulb connected in series in a circuit, what happens to those? Remember, for our purposes, we're going to be using light bulbs as our resistors to denote the resistors. So we should know that when the resistors are connected in series, there's only just one pathway for the current to flow, from one terminal through the wires, passing the resistors, and then back to the terminal. As we can see on this diagram here, the current is moving in just one continuous direction. There is only just one pathway that the current can follow if the resistors are connected in series. So we are saying that the resistors in series, they are called your potential dividers. That means the total voltage across the battery is equal to the sum of the voltages across each of the individual resistor. So that means in series, the voltage that is going to be measured across this one resistor plus the voltage measured across this second resistor is going, the sum of those two voltages is going to be equal to the sum, or is going to be equal to the total voltage of the cell or of the entire circuit. So if we have more than one resistor, in this case we have two, if we have 3 or 4 or even 5, each of those resistors will each have different, depending if whether they are identical or not. If they are identical, they will each have the same potential difference, or rather the same voltage across them. However, if they are different in terms of the resistance, should one resistor, like in this case now, let's use 2. should one resistor have a resistance of 2 ohms and the other one have a resistance of 4 ohms, they will each have different potential differences measured across each of those resistors. However, the sum of the potential difference measured across the 2 ohm resistor plus the sum of the potential difference measured across the 4 ohm resistor is going to be equal to the total potential difference of the circuit. Now, how is this going to be shared? The resistor with the least resistance is going to receive or is going to have the least potential difference across it. Now, the one with the most resistance will have the most potential difference across it. So that means for electrons, for them to be able to move through this resistor, it is going to be easier for them to move through the 2 ohm resistor as compared to the 4 ohm resistor, because remember, the resistance is the measure of the resistivity of the electrons. We are trying to measure how difficult it is for the electrons to pass through each resistor. In the 4 ohm resistor, there's more resistance, so therefore it's going to be difficult for the electrons to pass through that particular resistor. So because of that, more energy is going to be required to push the electrons from one point to the other point. Now, what is that energy that is required? It is going to be your potential difference. So in the 2 ohm resistor, you need less energy to be able to pass through the resistor as compared to the resistor number 4. That's where you need more energy, which is why those two potential differences in those two resistors are going to be different. But as we have said, the total is going to be the one that you're going to be having across resistor number 1 plus the one across resistor number 2. When connected then in parallel, the resistors or light bulbs, as we have said, that are connected in parallel, what happens to them? Number 1, we need to remember that if your circuit is a parallel circuit, that means there's going to be more than one pathway for the electrons to move, or rather for the electric current to move. As we can see on this diagram, once your charge gets to this point, it divides. Some of it has to go through this resistor and the other one has to go through the other resistor. So there's more than one pathway that is taken by the electrons moving from one point to the other. Now, the current dividers now, we're saying that the total current from the battery splits into smaller currents. As we can see, once your current gets to this point, it will split into 2. Some has to go through this resistor and the other one has to go through that other resistor. But at the end, when they all meet up again at this point, the current is going to be the same as the one that we had initially before the split. So, the current strength provided by the battery is equal to the sum of the current strength through each component of the resistor. We need to remember that in parallel, the potential in series, the potential difference, it divides. However, when we are talking about the parallel circuit, the current divides. In series, the current remains the same, but the potential difference, it divides. Whereas in parallel, the potential difference remains the same, but the current divides, which then means the current at this resistor plus the current at this resistor is going to be equal to the total current of the entire circuit. Moving on. Now, looking at the relationship between the resistance and voltage when we are connecting in series. The resistor with a higher resistance has a higher voltage across it. As we have said, more resistance means more energy will be required to push an electron from one point to the other point passing through that resistor. And then in parallel, again looking at it now, the relationship between the resistance and the current. The parallel branch with the highest resistance draws the weakest current. So that means the current will always look for the path with the least resistance. So the path with the least resistance is going to receive the greatest current. However, the one with the highest resistance is going to receive, as we can see, the weakest current. You always need to remember that current is always going to look for the path with the least resistance. In series, the resistor with a lower resistance has a smaller voltage across it. As we have said, Least resistance means less energy needed to push the electrons from one point to the other. However, in parallel, the branch with the lowest resistance has the strongest current. As we have said, current looks for the path with the least resistance. The one with the least resistance will receive the greatest current. The one with the most resistance will receive the least current. So that's what happens, or that is now the relationship between, in series, the resistance and the voltage, whereas in parallel, the relationship between the resistance and current. But then remember, in series, what is going to remain the same here? The current is going to remain the same at each and every point because there's only just one pathway for that particular current to follow. Whereas in this particular case, in parallel, what remains the same is going to be your potential difference. Now, in series, as you have said, current remains the same, and in parallel, the voltage is going to be the same. The current strength is the same throughout this series circuit. However, in parallel, the voltage across each parallel branch is going to be the same. Furthermore, components connected in series create a single pathway for the charges. As we have said, in series, there's only just one pathway for the charges to take, whereas in parallel, there's more than one. There could be two pathways, or there could be three, or even more. So there could be more there's actually more than one pathway for the charge to follow, moving from one point to the other point. Now, lastly, what you're going to be looking at now is the current strength going through each component is equal to the current strength of the whole circuit. As we have said, in series, the current remains the same at each and every point that you measure it from. Whereas in parallel, the voltage, the potential difference, it remains the same at whichever 2 points that you're measuring it from. Remember, for us to measure the voltage or the potential difference, you need to measure across 2 points, point A and point B. So in those 2 points that we are measuring at anywhere in our circuit, the voltage is always going to be the same. Right. The total resistance and the main current. So now in series, looking at the resistance and the current, the total resistance increases with every addition of a resistor in series. So the more we add resistors in series, the resistance of the circuit is going to be increased. Therefore, the main current strength will decrease accordingly. So because we are adding resistance in the circuit, the entire circuit is going to increase in terms of the resistance and therefore decrease in terms of the current strength because of the relationship between the resistance and the current, that when one increases, the other one is going to decrease. So in parallel, now looking at the total resistance and the main current. So the total resistance decreases with every addition of a resistor. So in parallel, whenever we add another resistor in parallel, the resistance of the circuit is going to be decreased. Therefore, the main current is going to increase accordingly. So whenever we are adding a resistor in parallel, we are actually decreasing the resistance of the entire circuit. And remember, because of the relationship between the resistance and the current, when we are decreasing the resistance, that simply means that the current is going to increase, provided that the potential difference in this case remains the same. Now, all of these that we have been talking about, the relationship between current, the voltage, and the resistance. Now, those things, they can be measured. They have certain symbols. Then the relationship between all of these things is called the Ohm's law. So now the quantities that we have resistance that has the symbol R, and the SI unit ohm with the symbol of omega, the symbol that we're using there. And then another quantity that we looked at was the voltage. Our voltage has a symbol V, capital letter V, and the SI unit is volt, and then the unit for that, or the symbol for that volt, is also going to be our capital letter V. And then lastly, our current has a symbol I, capital letter I, and we know that it's measured in amperes, so the SI unit of the current is amperes with a symbol capital letter A. So remember, the relationship between all of these three quantities is called the Ohm's law. So before now going on to the next concept, we're just going to go for a quick short break, and I will see you just after this.